Let's look at a couple series parallel AC problems for review. So here, let's just kind of talk through the solution on this one. So we've got, we're looking for I1, which appears to be the source current right there under the source, and then we're looking for V1, which is the voltage across our inductor. So first thing I think we'll do is we'll reduce this circuit down to a total impedance and use Ohm's law to find our source current, which is I1. So we want to identify the impedances we can combine. So notice that our inductor and R2 are connected on one side, and they are connected on the other side at ground. So that means they're in parallel. So we're going to combine R2 and XL in parallel, and we're using the equation here, the product over the sums method. So basically what we're doing is ZR2 times ZL over ZR2 plus ZL to give us this R2 in parallel with, let's see, I'm going to use Z instead. So ZR2 in parallel with ZL. And that's the equation we're using. So for our resistor, it's 20 at 0 degrees. Our inductor is 80 at 90 degrees. You could also use the rectangular form there. So 20 times 80J. And then the sum underneath is 20 plus 80J, or J80. It doesn't matter where the J is in that case. So you could do this all in rectangular form, or you could do this in polar form, or you could kind of mix and match as we've done here. Really doesn't matter. So what you get there is the combination of these two impedances is 18.82 plus 4.71J, or in polar form 19.4 at an angle of 14 degrees. Okay, once you combine those, let me see if I can do just a quick redraw just so you see kind of the shape of what's going on here. So now we've got this impedance here, which was ZR2 in parallel with ZL. So I'm going to call that Z1, just for lack of a better term here. And this is R1. And then we've still got our capacitor up here. But notice when we combined our inductor and R2, we now have a Z1 that's in series with R1. So the next step is we're going to add R1 to that. So we're adding our 10 ohm resistor, and that gives us 29.2 at 9 degrees, 9.27 degrees, or the rectangular form right here, 28.82. All right. So once we combine these impedances in our circuit, notice that will then be in parallel with our ZC. So we would then, So we would then combine what we just did, the two parallel, the resistor, inductor in parallel plus R1, then we would put that in parallel with X sub C. And what we end up there with there in polar form is 28.1 at an angle of negative 18.26. So that's going to allow us to use Ohm's law to solve for I1 right here. So I1, or the source current, is 1.4 amps at 18 degrees. All right, so there is the first thing we were looking for. Now we need V1. So notice that V1 is not only the voltage drop across my inductor right here, but since that's in parallel with R2, it's the voltage drop across R2 as well. So when I combined the two and I made that Z1, that's what I'm looking for. I'm looking for the voltage drop across Z1, which up here in my quick drawing is right here. So if you notice that 40 volts that we have at 0 degrees, that is going to be the voltage drop from here to here. So notice that's the voltage drop across my capacitor, and it's the voltage drop across my branch with the resistor R1 and Z1. So this becomes a voltage divider. So the portion of the voltage that I'm looking for, of course, is the voltage across Z1. So I'm going to use the equation, the voltage divider equation, where I take, for V1, I'm going to take Z1 over ZT times the total voltage across the divider. Now in this case, ZT is the impedance of this entire branch. It's not ZT of the circuit. So that's the ZT I'm looking for right here. And then Z1, of course, is right here. And the total voltage across both, in this case, would be the source voltage. It's not always the source voltage, but in this case, that's the voltage drop across the entire divider circuit. Okay, so I'm just going to label this the divider circuit. That's just going to be a portion of your circuit typically. All right, so that brings us to V1 is equal to our 19.4 at 14 degrees. Remember, that was up here. That was our Z1, if you recall. Oops. So that was Z1 divided by ZT. That is the total impedance of the divider circuit. That's right here. Again, it's not ZT of the circuit, it's ZT of the divider portion of the circuit. And then I'm going to multiply by the total voltage across both of those impedances, and that gives me 26.5 volts at 4.7 degrees. Now, the second part of this is I was asked to find the average power delivered to the circuit. Remember, that's going to be your RMS voltage times your RMS current times cosine theta, where theta, remember, is the difference in phase angle between the voltage and the current. So we're looking at E here. So the phase angle for E is 0, and I, and the phase angle there is 18.26. So the difference in phase angle is 18.26, and we're looking at the absolute value there. We're looking at the absolute value there because we'll account for which is leading or which is lagging when we talk about our power factor. So then our RMS voltage is 40 volts. Our RMS current was 1.4 that we just calculated. So that means we have an average power delivered to our circuit of 53.18 watts. And our power factor, remember, that's this argument right here, cosine theta, which in this case is cosine of 18.26 degrees. Again, I'm leaving off that negative sign. And let me quickly calculate this. So that's about 0.95 for our power factor, and we're told that that's a leading power factor right here. Leading just means that our current is leading our voltage, and if you notice, when we calculated our current, we found that it has a phase shift of 18.26. That's a positive phase shift to the left, and our phase shift for our current, for our voltage was 0. So the current is leading the voltage, and that's why we have a leading power factor here. So we would need to note that that's a leading power factor. All right, let's look at our next circuit. And here we want to find I1. That's the current through R1 all the way out to the right side there. All right, so the first thing we want to do is do kind of a reduce and return so that we can return back and find that current. So the first thing I would do is I would combine the capacitive impedance and R1, the impedance of R1. Those are in parallel. So that would give me, I'm just going to do a really quick redraw here with my inductor, capacitor, inductor, and then I'm just going to throw a block in here for what we call Z1. That's still XL2, XC1, XL1, and then our source I. And this is really just to give me a graphical representation of what we've got. So Z1 is going to be the parallel combination of ZC2 and ZR1. So if we do the product over the sums, that's going to be 2 at negative 90 degrees and 1 at 0. And then when I add these on the bottom, I like to start with the resistor because that's the real part of the equation, minus 2J. Again, you can also use rectangular form on the top or polar form on the bottom. It really doesn't matter as long as you can handle the math there. So that should give us about 0.89 at negative 26.57 degrees, or in rectangular form, 0.8 minus 0.4J. Okay, so there's Z1. The next step would be to combine Z1 and ZL2. So I would make this part, I would call this Z2. Okay, so Z2 would be ZL2 plus what we just found was Z1 right here. So if I add my 8J to 0.8 minus 0.4J, I get 0.8 plus 7.6J. Or if you want the polar form for that, it should be 7.64 at 84 degrees. All right. At this point, I would combine the Z2 and the ZC1, and we'll just call that Z3. So ZC1 in parallel with Z2. So that's going to go down here. So again, we could do product over the sums for that. So I've got a negative 2J for ZC1, and then I'm just going to put in the rectangular form here on the top. You could do either, but some calculators handle that better. Just make sure to put in Z2, you're putting the whole thing in parentheses and not multiplying by just the 0.8. Okay, so be careful about where you have your parentheses. And then on the bottom, I'm just going to sum them. All right, so that should give me 0.1 minus 2.7J, or in polar form, 2.7 at a negative 87.88 degrees. All right, so we're almost done. Now that gets us to our inductor, and then this Z3 out here. Again, I'm not redrawing everything, I just want to have, you know, a place where we can kind of track our steps back. So that would give us ZT, where we're going to take our ZL1 and now add that to the Z3 that we just found. Okay, so ZL1, that's 8J plus, and I'm just going to use the rectangular form here. So 0.1 plus 5.3J is the rectangular form, or about 5.3 at an angle of 88.92 degrees for ZT. All right, so we do all of that so that we can then find our source current. No, we have our source current. Okay, so our source current is here. So that 0.5 amps, that's going to be, let me switch to red here, that's right here. So what happens there, actually let me go up to our second circuit. That 0.5 amps is right here. And what we have here is a current divider, where the two branches of our current divider are the capacitive branch and then this inductor L1 branch. And then of course it comes back together on the other end to be 0.5 amps. So I'm going to treat this like a current divider, where this is branch 1 and this is branch 2. So it's just a 2-branch current divider. And I want to find the current over here, okay, because that's going to be this current that I'm looking for. And I'm going to call that maybe I prime, I1. Okay, so I prime for the current divider rule. I'm going to take, I'm going to use the equation where if we're looking for the branch current over here, then I'm going to look at this ZC1 on the top, and then the sum of ZC1 plus my Z2. Remember over here, this was Z2 for this branch, and this is ZC1 for this branch, so that's why I'm using those two. That's the those are the impedances of my current divider. And then I'm going to multiply by the 0.5 amps coming in, and that's at 0 degrees, so I'm just leaving off the 0. So ZC1, remember, was 2 at negative 90 degrees. And then when I add ZC1 plus Z2, I'm going to use rectangular form here, I think. So minus 2J plus my Z2 up here, 0.8 plus 7.6J times 0.5 amps. And so when you do the math to work that out, it's about 0.177 at negative 171.87 degrees. Okay, so that I prime, again, is right up here. Now, what happens at this point is we have another current divider. This time, branch 1 would be here, or 2, it doesn't matter which, and the other branch is over here with through the resistor. So this would be my current divider out here. So the total impedance of the current divider is the parallel impedance of the capacitor and R1, and the current coming in would of course be I1 up here. And so I'm going to use the current divider rule again. Let's call that actually I1 because that's what we're looking for. But remember, to find that, I'm going to take this impedance over the sum times the current coming in. Okay, so that would be ZC2 over ZC2 plus ZR1 times that I prime that we just found. Okay, so ZC2 would be the 2 at negative 90. And then on the bottom, I'm going to switch to rectangular form plus 1 times the 0.177 at negative 171.87 degrees. And that means that I1 should be 0.158 or 158 milliamps at 161.57 degrees. And there's my I1. So we found I1 for our series parallel circuit. So review your equations. For instance, when you have 2 branches in parallel, let's say we've got Z1 and Z2. If you're looking for ZT, you can do a product over the sums, Z1 times Z2 over Z1 plus Z2. If you're looking for the current divider rule, so I1, which would be right here, you would take Z2 over Z1 plus Z2 times whatever the total IT coming in would be. I2 would be the opposite. You would take Z1 over Z1 plus Z2 times that same total. So kind of review your equations. These short little equations like this will help you immensely with the AC calculations. They're a little bit easier to use than the original equations you learned. However, the original equations work and you can use those. I just wanted to highlight some of the shortcuts that we like to use with AC.